Computers process instructions linearly, moving from one command to the next. But when operations are nested inside one another, a pure linear approach breaks down. The system needs a way to pause the current task, execute the nested instruction, and then resume the original task in the exact right order. If a processing engine only reads forward, it cannot handle recursive logic. When it encounters a nested command, it loses its place because it has no structural memory of the previous execution state. This animation shows a parser reading the mathematical string 2 plus 2 times 3, 2 plus 2 plus 3. When it hits the inner parentheses, it must evaluate that expression first. Without a memory buffer for the outer layers, the parser cannot resolve the deepest parts of the equation. To solve this, the architecture requires a specialized memory protocol. We need a system capable of temporarily storing these suspended states and then reversing them in the correct sequence once the inner operations are complete. Resolving nested complexity means abandoning pure forward linear execution. Instead, the system relies on a dedicated state reversal mechanism to trace its steps backward. The specific state reversal protocol required for this task is called LIFO, which stands for last in, first out. This means the last piece of data suspended is the very first one resolved. The data structure that mathematically enforces this LIFO protocol is called a stack. A stack restricts memory access so that data can only be added or removed from a single point, known as the top. Today, we are going to construct a robust stack architecture using the simplest memory structure available in computer programming, a contiguous array. We will define the strict boundary logic of this array, implement the raw C++ class, and prove how it achieves O1 time complexity. O1, or constant time, means the operation takes the same amount of time regardless of how much data is in the structure. By enforcing strict operational rules on simple linear arrays, we provide the predictable memory management required for modern compilers. This diagram shows our foundational building block, an array allocated as a contiguous, physically unbroken block of fixed memory. Here we have a 5-slot grid, labeled with indices 0 through 4. Because an array is fixed in size, we must define max. This represents the architectural constraint on our memory allocation. To make this function as a stack, we introduce the integer variable top. This acts as an index tracker, pointing to the most recently inserted element. Initially, top is set to -1, pointing outside the valid 0 to 4 array indices. Because indexing starts at 0, -1 indicates that no valid array indexed is currently occupied by data. Every subsequent insertion, deletion, and read operation we perform will strictly rely on manipulating this single integer variable. An array becomes a stack not through physical changes to the memory blocks, but by restricting how we access that data using the sliding top index. The push operation is the method for inserting a new element at the peak of the stack's current state. Before we can push new data, we must check for a boundary condition, stack overflow. This occurs when the fixed array has reached its maximum capacity. As seen in this logic diagram, the algorithmic check for overflow is evaluating if top is equal to max -1. If top has reached the final index of the array, the system rejects the insertion to prevent unauthorized memory access. If the stack is not full, the push sequence begins by incrementing the top pointer by 1. Step 2 is assigning the new data to the array, strictly at that newly updated top index. If we run consecutive push operations to insert 20 and 30, the top pointer advances through the indices without shifting any of the previously stored data. Because we are not iterating through the array or sliding elements to make room, the time complexity remains constant. The push operation achieves O of 1 time complexity because it relies purely on a single pointer increment and a direct memory address assignment. To reverse the state, we use the pop operation. This retrieves and removes the most recently added element. Pop must check for its own boundary condition, stack underflow. This is triggered when the system attempts to extract an item while top is equal to -1. This sequence shows a successful pop happening in 2 steps. First, we extract the data at stack of top. Then we decrement the top pointer. Notice what happens to the physical memory. The value 30 still exists in index 2. This is called logical deletion. Because the data sits above the active top pointer, it is inaccessible to stack operations. The next push command will simply overwrite it. This is different from the peek operation. Peek reads the value at stack of top without modifying the pointer. Actively erasing physical memory would require extra CPU cycles. By controlling the index pointer instead, we guarantee O of 1 state reversal. We can translate these abstract algorithmic steps into a concrete class implementation using C++. Examining the constructor of our class, we can verify that the instantiation of the stack correctly defaults our pointer. Top is assigned the starting value of -1. The syntax for the push method is concise. The instruction ARR++ top equals X uses a pre-increment operator to update the index immediately before placing the value into the array. The pop method uses mirrored syntax with a post-decrement operator. The instruction return ARR top ---- returns the value at the current index and then decreases the pointer value. These unary increment and decrement operators allow developers to combine pointer math and array access into a single instruction cycle. Mastering this underlying pointer math allows software engineers to seamlessly translate abstract LIFO theories into optimized, low-overhead code. Looking at systems architecture, we must consider why we choose fixed arrays over dynamic memory allocation, which can grow as needed. The primary hardware advantage of the array stack is superior CPU cache locality. CPU cache locality is the tendency of a processor to access memory addresses that are physically close to each other. Because the array is a contiguous block, the hardware can process it efficiently. This diagram compares the strict contiguous layout against a linked list stack. The array is a single unbroken block, while the linked list relies on fragmented memory nodes scattered across the heap, connected by individual pointers. However, the array approach has a significant drawback. The rigid max ceiling can lead to unutilized memory. If you allocate space for 100 elements but only use 10, the remaining space is reserved but empty. There is also the risk of overflow. If the execution states suddenly exceed the pre-allocated array bounds, the stack runs out of room and the program fails. Array stacks trade dynamic flexibility for operational speed. This makes them the optimal choice for systems with predictable workloads, where performance is the primary requirement. This data structure serves as the foundational architecture for modern computing environments. Programming languages map nested function executions, like a main function calling func_a, into an identical call stack architecture to track the return address once a function finishes. Common software features like the undo and redo commands rely on strict LIFO state management to sequentially reverse the user's actions. In technical interviews and algorithmic problem solving, engineers use monotonic stacks. A monotonic stack is a variation that maintains its elements in a strictly increasing or decreasing order. This animation shows how an array stack resolves the next greater element problem for the array 4, 5, 2, 10. Tracking these values in a stack reduces a brute force search from O of n squared down to a single O of n pass. The array stack proves a core principle of computer science. By applying rigid mathematical constraints to simple contiguous memory, we create deterministic engines capable of managing the most complex nested logic in existence.